Yeah, just double check. Yeah, well, lovely. Well, thank you all for coming. This is a good thing. I mean, this is basically something that she's been the lead on this, that we were doing with Tim's group. So it's a little case study, and it's using multiple imputation, which is something that's increasingly used these days, particularly, you know, with computing having gone on. So if I just press the button. I press the
No, correct.
right. So just a resume about missing data. There's various forms or assumptions that we make about it, and one assumption that some people make is missing completely at random. So if something is missing, it has no relationship to anything else, either in the data set or not in the data set. It is completely at random. So that is one assumption that can be made. A more common assumption is that the data missingness relates to something in the data. So, you know, it might be we're missing older people, or might be people who don't have transport, but it's something that we've measured that we could use to estimate the value that's missing. So that's missing at random. The one that you don't want, and it's actually possible to test this, is missing not at random, where the outcome variable, the value of the outcome variable is related to the missingness. And a few examples are there on the right. It may be some people don't want to reveal their income. It might be, you know, on very low or very high incomes, they may not be revealing that. So that's related to the size of income. So the size of the missing variable itself might be blood pressure. Perhaps people are less inclined to measure people's blood pressure if it's particularly low. They might be more interested in high blood pressure and depression. Perhaps people are dropping out because they don't think the treatments work. They may be a bit more depressed than the people who are staying in. So they are missing data mechanisms that we can have, which are determining what sort of model we might use. And over the years, there's been various approaches to missing data. Some people just use complete cases, so ignore all the people who have missing data, which is rather wasteful. Some people just replaced with an overall mean. You can also use algorithms that are like regression, in that they use existing data that we got on them to estimate what is actually missing, the missing variable of interest. Single imputation, we just put one value in. What we're talking about today is putting multiple values in by basically looking at random sampling variability. There are also Bayesian approaches. If you do Bayesian, they will also look at missing data and include people who have missing data. So that's the big thing about all of this. In the past, when we had time data, so repeated measures, people would put in the last recorded observation. You generally had at least baseline data, so you could put in the actual baseline value at least. That is becoming a bit frowned upon. A lot of studies have said there are better approaches used. Random effect models, which are like the EM algorithm, they use all the data, but they just use the data once, as it were. Now, another issue is how much data we've got missing, what percentage of observations are missing. And there are rules of thumb about how important it is to use particular methods of missingness to account for missingness, depending on how much is missing. If we don't have much missing, we can do any of these. It doesn't matter which, they're all going to give reasonable answers. And Tabachnik and Fidel, which is one of our sort of cortex or multivariate data, they say you've got less than 5% missing, it doesn't matter what you do, even use perhaps even complete cases there. There are other rules of thumb. I mean, this strikes me as a bit liberal, but there is a reference there that says even up to 20%, you can just use the overall mean. So that's something that we can consider when we're deciding how we're going to replace the missing data, how much of it is actually missing. Now, we're now getting into what methods we might be using in our particular study. And there's something called random forests, which is a way of using existing data that we've observed, so missing at random, we're assuming what is missing relates to what we've got which isn't missing. We can use that to estimate it. And there's a random forest which is used when we have continuous variable where we've got missing data on that. And it basically works out what relates to what and uses that to estimate what is missing, fills in the gap, physical number put in there, and then it refines it somewhat to try and get an accurate representation. And so we fill within the data. Now, the imputation does, it fills in the blanks, so we have complete data of what we've observed and what has been estimated using the observed features. And we can, it's like a regression, and we can do it for continuous missing data as well as binary missing data. And we have some examples of that coming up. So this is just a real resume of what I've said. We're using the data that we've already got to estimate data that we don't have. And with multiple imputation, we're doing this a lot of times. So each time we fill in the data and we fit the model to the data. I mean, there's a lot of time. Each time we had a random component, so the missing data values differ between each go that we use, each imputation. Each time we fit the model, and we get all these models fitted separately to each particular data set, and we combine them to get an overall figure at the end. And the idea is it takes into account sampling variability in our data. So that is hopefully a summary of that slide. The bottom part on the right asks the question, how many imputations should we use? How many random samples estimating the missingness should we use? The traditional number was to make the number of imputations equal to the percentage missing of observation. That was Bodner. But in more recent times, it has been suggested that you actually need to have more than the actual percentage missing if you've got large, and again, you know, what is large numbers of missing data. But you can in the algorithm, you can just put in how many imputations you want and how many different data sets you want to generate. So that's that. So we've got multiple imputation. This is, again, I'm really just repeating myself here. We're generating multiple building data sets so that missing values have been replaced by estimated values. And we're going to fit our models. In this case, we're doing anchovers, get all the coefficients out, but each time for each data set, and then it magically combines everything to get the overall result, which we then quote. That's the end product, an overall averaged regression estimate that addresses the question of interest. Now, what is the case study? What are we looking at? It's two groups, two arms, which are control, which is light exercise, and we've got mindfulness, which is a sort of meditation process. And what we're interested in is people's work effectiveness. And there's a particular scale, work effectiveness. We ask people to, you know, a scale of 0 to 4 to make various responses. 240 recruits, intention to treat, that's the big buzz thing that we always have to do. We've got protocol, use the data that we've actually got. Intention to treat, it might be complete cases, might be protocol. Intention to treat uses everyone, those people who we haven't got data on. So multiple imputation is a means of using all the data, and that's why it's called intention to treat. And most journals want intention to treat, but some people do both and just make sure, you know, what the missing data is having an effect on. And so basically on the right is what I've just said, so I don't think I need to say anything about that. Primary outcome variable is this variable work well functioning, and in this questionnaire there's a lot of items in 25, and it's on a ordered scale going from 0 to 4, which is it's difficult to none of the time this is difficult to, I might be looking at resources, what facilities have you got, is it easy to use the facilities? So basically the higher the score, the better, means that you're more effective at work as you perceive it, subjective measure. Goes from 0 to 100, so higher scores are better. The arms of the trial, as I just mentioned earlier, is basically like physical exercise as the control group, so it's not a passive control group. People are actually having to do various exercises, and the other one is a mindfulness, so it's not physical. It's basically meditation, and these people are doing it every day, and they set reminders to do these things. So we assume that they're doing them, and the various setups there, various ways of these things being learned, and you've got your teachers, and you've also got various media that people can follow in order to do their meditation. So we've got the two arms, control versus the intervention, and then we can look at the data that we've got, looking at this work variable, and what we're interested in is people's work effectiveness as they see it differing between the light exercise group and the mindfulness. So is mindfulness helping? So that's what we're interested in, the two groups. People are allocated randomly to each group, and these assessments are done baseline. You've got 4 weeks after it's all started, so post-intervention, and there's one follow-up, which is 12 weeks from baseline. So there's 3 time points, and we're interested in comparing the work score at each of these time points, adjusting for baseline. So we've got baseline in the model, on the model, and we're also going to have employment status in the model, which is local authority, a lot of people from local authorities versus the rest. And why do we put that in? Because they vary between the arms. Even if we randomly allocate, occasionally we get things that. So that's our model, over model. So this work variable is the outcome. So we can look at the data we've got. Usual assumptions. Does it look normal? Do our box plot, does that look normal? Well, yes. Answer that, and then we can get into the imputation. In this study, each group, each arm was imputed separately. Okay, so we do the light exercise, we fill in the blanks for that, then we put in the blanks for the intervention, which is mindfulness. We do on the left, and then we just fit the model. We ask for now this score there goes from 0 to 100, so it's continuous. So we do the random false, the RF, and then we generate the data sets, 100 data sets, and you can also specify a large number of iterations to make sure that the values are properly worked out, because it's quite a bit going on there. And so that's in the bottom right part there. So that is creating the data sets there. And we can have a look at the data sets. The blue bit is the imputed data set. I mean, it's sort of in the middle of all the observed data, and you can make these sort of check. And this is the 4 weeks after baseline. So this is post intervention, and we can see in the 2 arms there, then the control arm, light exercise, and the other arm, which is the mindfulness. And we can also look across the 100 imputations, looking at values of this work variable post-intervention, and just see, the blue bit, which is not always easy to see on the left there, how typical that is of all the other, how variable the values are in the filled-in data set. So is there a difference between the arms? Do a regression with the with command. So we've now we've produced all the data sets. We now fit the model to each one, fit the ANCOVA to each one. We get all these numbers coming out, you know, we get, I think it's about 4 numbers for each of the regression estimates for each imputed data set. So 4 times 100. And then pool them, summary pool, there we are on the right. And we go straight to AS factor arm. Is there a difference in the people's work effectiveness in the control intervention, light exercise versus mindfulness? And we can see the p-value 0.14, so there's no difference. So you might as well just do light exercise as opposed to meditation. So that would be our result. And so we've got our t-value in there, which is quite a handy thing as well. You can also get out summaries of the imputations coming out there, how much data is missing. Quite a bit of data missing, as it turns out. Between 40 and 60% data is missing there. And then when we actually report this, we report it Cohen's D, it's what we normally do, convert T to D using the formula there, and just get the p-value. So that's the summary. D and P, just to say there is no difference between the two groups. We can do it for logistic regression. So we've got a work and social adjustment scale. People reported any health problems, and it turned out most people didn't have any health problems, and there were quite some people who had a lot of them. So we basically dichotomized it, no health problems versus the rest. Dichotomous, do it all over again. Generate the data set. We use log regression, so the outcome, the missing variable, is replaced by a 0, 1, because the actual thing we replace is 0, 1, and there we all are coming out there. So that's just the first 2 and a bit imputations of what's produced there. And it just follows through as it did before, 100 data sets, 100 billion data sets. And you can specify a seed for it. So the seed is, you know, which particular randomization has been used. That's logistic regression again. So we're combining now the estimates for each data set. Well, we're doing the estimation for each one with the width, pool them, summary pool, there we have on the right. And is there a difference in, you know, people's ability to work in the mindfulness versus the light exercise? Well, no, there isn't. 155 for the p-value there. So, other things, well, you know, you can compare intention to treat using the built-in data with the, you know, the actual raw data. If there are distributional problems, you can do Quade's test, which is ranking the outcomes, so ranking our work scale, and do that. And of course, we can also adjust for assumptions, you know, non-normality in a scale as we would normally do by doing our transforms, and then that carries through to the imputations. Now, there was an additional thing here, which was the fact that people can produce results, produce their work score more than once a day. They're prompted more than once a day. So this is a typical example. 1018 is a person, and they produced, I can see work score, they've got about 6 or 7 values there, but there's a lot where they aren't producing results there. So you've got a clustering going on because you've got people producing multiple work scores on a you know, well, using multiple work scores, we can see there. So the question then is, can we actually go around filling in the blanks when we've got this repeated method set up? And the answer is yes, you can. And this is describing it there. Again, do each arm set each person is in light exercise or doing the meditation. And you can just estimate each person separately now, and put in the blank from their work total score, and then just do the modelling there with the clustering there on the person, and you end up again with the pooled estimate. So we got with and pooled in the game there. Quite a lot of missing observations, as you might have noticed there. That's an interesting point. I mean, I've not come across anything that says, you know, there's an upper limit on how many people you can, you know, how much percentage missing you can have. Summaries now. So we basically, you know, we do this for these well-known statistical procedures. You can do it also in mediation, because mediation is just a collection of regressions. We're doing the pooling there. We could do this when we had two groups, because it just comes out as a regression estimate. The R is a regression estimate comparing the two things. So that came out at the end there. But if you have three or more, of course, you need to have 2/3 in the model. So more of a thing to think about there. You don't have to use the same variables to impute. You can specify different sets of variables, different, you know, you might have either age and gender for the control group to estimate your work outcome, or you might have employment status and something else in the other group. So you can vary that. Oh, the computer can work it out for you, as it did here. I mentioned about repeated measures on the last slide. You can do it within a person, and it's always nice to have a bit of validation, isn't it? And we did check it in SPSS. What we did, you can't produce the same data because it's all done on randomness. So, you know, each data will differ from the other data set. But what you can do is check the pooling. And we got the same results pooling in R as we did pooling data, the same data in SPSS. So that was good that the pooling was working there. And you can actually pool F ratios in SPSS, i.e. when you have 3 or more groups. And of course, the result of the study, well, I've already sort of intimated that as I've gone along. But in terms of retention rate, it's fairly typical. 2/3 stayed after 4 weeks and moved after 30 for the 12 weeks. And there was no effect of doing the meditation. So the meditation didn't differ from light exercise, and that's how we presented it there in terms of the coincidences. But I mean, basically 0.06 and 0.02 were low there. So that was the result of the study there. And it was just from the pooling over the data set. And that is it.